Thank you. So last time I started telling you about long-range percolation. Before I get back into that, I want to just go backwards a bit and tell you something that I forgot to tell you, which was another heuristic argument for why the critical dimension is 6. So, we saw one not very convincing argument, perhaps. Well, it depends, but was that, there's this triangle condition, which is a sufficient condition for mean field critical behavior. And we saw, or I left it as an exercise rather, that if you look at the triangle diagram for the random walk Green's function, then that's finite, if and only if you're in strictly more than 6 dimensions. On the other hand, for self-avoiding walk, I think many people will prefer, this kind of heuristic, like, okay, the reason why self-avoiding walk begins to behave in like a Brownian way, or like in a similar to simple random walk way above 4 dimensions, is that the simple random walk is like not really intersecting itself macroscopically. And, in particular, 2 independent simple random walks will intersect only finitely often, almost surely. So you can ask, is there a similar kind of heuristic like that for percolation? Also, how could you heuristically guess that 4 is the correct dimension for that for a simple random walk, right? And there's a sort of powerful and very easy to implement heuristic technique for understanding these kind of problems. So the rough heuristic is that if you have an A-dimensional random object and a B-dimensional random object, this is not a definition, right? I'm not going to say what this means. And you can ask, when do they intersect, typically? Well, it's roughly according to if A plus B is bigger than D, then they will typically intersect. If A plus B is less than D, then they won't. And of course, the boundary case can be a bit subtle and maybe depends on finer details. Okay, now let's see some examples of this. So, okay, the first thing you have to say, of course, is, okay, for my favorite random object, like what is its dimension, right? And one way you can often think about this, well, there are a few different ways. So one would be, if you take your random, maybe it's your random set, S is your object, right? And you intersect it with the ball of radius R, maybe this is going to go roughly like this sort of fractal dimension, right? Maybe that's a reasonable thing. And of course, if you look at this in expectation, then this is the same as saying like the probability, maybe this set depends on a choice of base point, right? Maybe this is S of the origin, right? Like a simple random walk started at the origin or a percolation cluster at the origin, right? So you could say, this should be roughly the same, at least if the expectation is giving you the right answer, as saying this, right? So in particular, the exponent for the 2-point function should be kind of maybe telling you the dimension of the object, and that will at least be the right thing in high dimensions. So in particular, simple random walk, you should think of as a 2-dimensional object, right? If you look at how many points in the walk intersect the box, it's going to grow like R squared. Of course, in low dimensions, that's not true because there's like not enough space for it to be true, right? But you should think that these objects like want to have this dimension, and they will have it once you're in a high enough dimension to let them fully express themselves, right? So simple random walk is 1-dimensional. Of course, you could look at a line, which will be 1-dimensional. A point will be 0-dimensional. So here's an example, recurrence and transience, right? When does a random walk return to the origin infinitely often? Well, you're exactly asking, when does a 2-dimensional object intersect a 0-dimensional object, right? So recurrence transience. Right, so the critical dimension, right, for a random walk returning to the origin infinitely often is 2. Okay, of course, this is not a proof, but you probably all know this theorem, and this is one way to think about that will generalize to many other situations, right? If you want to look at when does a simple random walk intersect a line, well, it's 2 plus 1, it's 3. Of course, this is easy to prove from the recurrence transience theorem, because if you just project onto the orthogonal complement at the line, then you're doing a random walk in one less dimension. But still, it's good to have these heuristic methods because they generalize much more. Okay, and of course, 2 simple random walks is 2 plus 2 equals 4. So that's why 4 is the critical dimension for a self-voiding walk. Okay. So how should we, interpret this for percolation? Well, as I said, we want to think of percolation as like a branching random walk, a self-interacting version of branching random walk, or at least that's the right intuition to have in high dimensions. So what's the dimension of branching random walk? Well, of course, actually this becomes not quite the right thing for something like branching random walk, or indeed for percolation, because percolation is actually dying, right? When you it's unlikely to reach the boundary of the ball. So really, when you look at this kind of this 2-point function thing to get the right answer for the fractal dimension, you should be saying, okay, if I condition on reaching a given distance, right? So in particular, for branching random walk, you don't really want to, of course, this 2-point function for branching random walk is just the same as the simple random walk one, right, by linearity of expectation. But branching random walk is, you shouldn't think of it as 2-dimensional. You should think of it as 4-dimensional. Okay. And there's a few different ways of seeing that. So one thing you can do is you can actually define what you might call the incipient infinite critical branching random walk. So in other words, there's a well-defined way to condition, you condition to survive for R generations, you send R to infinity. That actually has a well-defined limit. So, you can't just condition on surviving forever because that has 0 probability, but you can condition on that or a variety of other, events and take limits, and you'll get a well-defined limit object that doesn't depend on the details of how you did the conditioning. Okay, and when you do that, this object will take up R to the 4 amount of space. And the way you should think of this 4 coming is really that, you get this genealogical tree of the branching random walk, and this has quadratic volume growth. When you condition it to survive forever, it's this incipient infinite branching process. This has quadratic volume growth. And that's basically because, the probability you survive for R generations in a branching process is 1/R. So when you condition on that, you increase the expectation by a factor of R. And, the expected number of particles starts off being 1 at criticality in every generation. So when you do the conditioning, it becomes R, where R is the number of generations. So you get quadratic volume growth when you integrate the linear function, right? Then what you're doing is you're embedding that branching process into space using random walks. So that has the effect of doubling the dimension because of the Brownian scaling, right? So you can think 4 is 2 times 2. It's the 2 from the growth of the branching process times the 2 from the Brownian scaling. Okay. So, so in particular, for example, if you say like when do 2 branching random walks like conditioned to live forever, when do they intersect a lot? Well, it will be in the critical dimension will be 8, right? Which of course is not 6. So, let's go back to this formula we had for the derivative of the susceptibility in percolation. Right, so we saw this last time. We have the cluster at the origin, the cluster at the other endpoints at the edge. right, on the event that they're distinct. Okay, and as I was explaining last time, there's a way we can kind of sample this pair of clusters, right, by saying, well, first sample this cluster, then sample an independent cluster here, but you're only allowed to connect to things that are not blocked by the other cluster. Okay, so naively you might think, well, the critical, and I want to understand when is this expectation basically the same as when they're independent, right? Or like if I didn't do this blocking, right? And naively you might think, well, it should be 8 dimensions, like that's the dimension at which these two clusters don't really intersect very much. Of course, I keep telling you it's 6, so this is not the right answer. Now, 8 dimensions actually is the correct upper critical dimension for a number of other models in which this non-intersection is actually the mechanism that's driving things. So, for example, there's something called lattice animals, which just means you pick a connected subgraph with n vertices uniformly at random containing the origin. And for lattice animals, it is exactly, this heuristic is correct. 8 is the critical dimension, and it's because it's when these connected subgraphs don't intersect typically. For percolation, something slightly different is happening, which is that the point is, of course, it doesn't really matter if these two clusters intersect, as long as most of the mass of this cluster is visible from this point without being cut off by this path, by this second cluster. Right, so what is actually the key thing? Well, we want that if we sum over the choice of the other points in the second cluster, that with good probability, this path, the open path, or an open path connecting the origin to this point is not intersected. Right? If I have that for a good proportion of the vertices here, that's fine to get this expectation to be of the correct order. It doesn't really matter if these clusters are intersecting somewhere in their kind of fringes. Right? So the key thing is not really that this cluster doesn't intersect this cluster, it's that this cluster does not intersect the path between two typical points in the second cluster. Okay. Now, the idea is that, again, thinking that we want to view this as a branching random walk plus an interaction. Of course, in a branching random walk, the path is just a random walk, right? So what this means is that the correct thing to think about is not really whether a branching random walk intersects another branching random walk. It's when does a branching random walk intersect a simple random walk, right? So this gives you 4 for the branching random walk and 2 for the simple random walk, which is why you get 6. Okay, is that plausible at least? Of course, this is again not a proof, right? But it's how can you see why the critical dimension of percolation is 6 from this kind of dimensional calculus kind of consideration? Okay, good. So maybe I'll just quickly mention that there's another nice way of computing the critical dimension, which I like, which I think I don't quite have time to go into in detail, but there's an important, again, heuristic theory, although it's something we can prove in various cases, of what's called scaling and hyperscaling theory. So the idea is that the critical exponents, I kept talking about 3 of them, but of course there are a lot that you can define, and they satisfy many relations between them, right? So there are relations which are satisfied in all dimensions, which are called the scaling relations, and there are relations that are only satisfied below the upper critical dimension, which are called the hyperscaling relations. An example of a hyperscaling relation, by the way, if that sounds like something scary, is if you have 2 points at distance n, you say what's the probability they're connected. In low dimensions, it will be roughly the same as the probability that they both connect to distance n over 4, say, which is, of course, okay. This relation is true in low dimensions, but not in high dimensions. So the distinction is basically that there's an important qualitative distinction between low and high dimensions for percolation, in addition to these things about exponents changing and so on, which is that in low dimensions, if you look at a big box at criticality, there should be a sort of tight number of large clusters. So for example, if you look at the number of clusters that intersect both sides of the box or something like that. that will be order 1 in low dimensions, but it will actually be divergently large in high dimensions. So, if you do something like compute the expected size of the cluster at the origin or second moment or something, in low dimensions, that will be roughly the same as saying the size of the largest cluster times the probability that the origin belongs to the largest cluster, whereas, size to the appropriate power, I should say. Whereas in high dimensions, you should imagine you have more like the soup of like a lot of large-ish clusters. So what happens in high dimensions is that if you take a large box, there are like r to the d minus 6 clusters of size r to the 4. And the largest cluster should be larger by a log factor or something, but it's not really important to anything. So yeah, so you get this distinction like in low dimensions, if both clusters like connect to the right distance, then they have a good probability of being connected to each other. In high dimensions, they don't. And so this gives you a relation between two critical exponents. And what you can then do is you can say, well, presumably at the critical dimension. So the weakness in this argument, I think, is that it's not really obvious that the dimension at which the hyperscaling relations break down is the same dimension at which you start to have mean field critical behavior, right? Like maybe you have like 2 different critical dimensions. Okay, but if you accept that probably there's just one critical dimension, then you can compute it by saying, well, at that critical dimension, I should both have the mean field exponent should be valid and the hyperscaling relation should be true, right? So, what is this? Well, in mean field, this is n to the minus d plus 2, right? What is this in mean field? Well, it should be the probability that a branching random walk reaches distance r, or n, sorry, squared, right? Well, to reach Euclidean distance n, roughly, you have to survive to n squared generations, again, because of the Brownian scaling, right? So for a branching process to survive for n generations, it's like 1 over n. So this guy here is like 1 over n squared, right? So in other words, it's n to the minus 4. Okay, so again, these are the mean field values of these 2 exponents. At the critical dimension, probably, I mean, there should be some logs or something, right? But you should have that the exponents still satisfy the hyperscaling relations. We're kind of assuming continuity in the dimension or something like that. Again, this is certainly not a proof, but you expect that you have the mean field exponents and they satisfy the hyperscaling relations. So of course, that should mean that minus d plus 2 equals 4, so d equals 8. I said I didn't have time to explain it, but I guess I did. Okay, so that now you've seen 3 different reasons why you should think the critical dimension is 6. Okay. Okay, so any questions about that? Otherwise, I'll move back to talking about long range. Yes, thank you. Okay, all right, so let's go back to long range percolation. So remember, we were putting an edge between x and y with this probability where we'll take j to be of this form, some power law decay. Okay. And, as before, we'll define beta c to be the infemal value of beta such that infinite clusters exist. Okay. So of course, as with percolation, as with nearest neighbor percolation rather, the first question you might want to understand is like, when is the phase transition non-trivial? So we were talking last time about, we had this quantity j, which now I can write in this form, right? And this is finite if alpha is positive. And we saw that beta c, well, I said that it's essentially the same argument as the one we did for graphs. Beta c is at least 1 over j. Okay, so it's positive. Okay. So again, the more interesting question is when is it finite, right? Which is the analog of PC being less than 1, right? And this theorem is that beta c is finite if and only if either d is at least 2 or d equals 1 and alpha is less than or equal to 1. Probably, yeah. Sorry. Okay. So of course, the case where d is at least 2, this case actually just follows from the nearest neighbor case, right? Because you can think that each pair of nearest neighbors has some probability to be present, right? So I have just more edges for matching p and beta appropriately in the long range model than in the short range model. But what happens now is that you can actually get a phase transition even in 1 dimension, in contrast to nearest neighbor models. Okay, and I think the right credit for this theorem is Newman and Schulman. Although I should say that, as with several of these early things in percolation, there's often an Ising model result, which was proven like decades earlier and is equivalent. So I don't know why people kept writing these. Maybe this is what I guess this just wasn't realized that they're equivalent until I guess that's really the work of FK and G and the introduction of the random cluster model and so on. So yeah. So in the context of the Ising model, I think this was done by Dyson in the 60s. Okay. In any case, the point is we can still have a phase transition even in 1 dimension when alpha is small enough. Okay. Now, one thing that I think can be quite surprising if you haven't thought about these things before is that, it may seem that we took our nice nearest neighbor percolation, very like canonical seeming model, and then we attached some additional like bells and whistles to it, and we made a more complicated model for ourselves. But in fact, the model is actually significantly easier to understand in various regimes. And it tends to get easier the smaller alpha is, which is like the more long range you are, right? And so one very nice instance of this is the theorem of Nurnberger from 2002. So what he proved is that if alpha is strictly less than d, and I'm always taking alpha positive, then there are no infinite clusters at etc. Okay. So of course, this is something we would very much like to be able to prove for nearest neighbor models. And maybe I'll add, I'll come back to saying more about this soon, but I was talking yesterday about this kind of phase diagram, right, where you get the effectively long range, short range, etc. And this line alpha equals d is actually sort of here. So, Noem's theorem actually applies to a bunch of models which are actually should be in the same universality class as the nearest neighbor short range model. So in particular, if you take d equals 3, alpha is 2.5, that model conjecturally is in the same universality class as nearest neighbor three-dimensional percolation. We can prove for that model that there's no percolation at criticality. Now, the conjecture is that if d is at least 2, this is always true. So you should never have percolation at the critical point. But It's also a theorem of Eisenman and Newman from the 80s that if D equals alpha equals 1, then there do exist infinite clusters. Okay. So you should think that this D equals alpha equals 1 point, it's right on the boundary of having a phase transition at all. If you have any larger value of alpha in one dimension, you just won't have a phase transition anymore. And this thing right on the boundary is having this special behavior. It's what we would call a discontinuous phase transition. So it's really behaving very differently than all the other points, at least conjecturally. Okay, so in that sense, this theorem of Berger cannot be improved for general D. And one of the things we may see is that like a lot of the techniques that you have, they tend to only really see D and alpha through the ratio of alpha to D. So you need to, if you want to like prove this conjecture, for example, you need a method which uses the value of D and not just the value of alpha over D. Okay. Okay. Um, Good. So I should mention this theorem of Berger. The proof is it doesn't really tell you anything about critical percolation, other than that there are no infinite clusters. The way it works is by saying, suppose you're at some value of beta where you have an infinite cluster, then you'll still have an infinite cluster at some beta minus epsilon, right? So it's more like it's a proof by analysis of the supercritical phase rather than by analysis of the critical phase, if you like. My first sort of introduction to this field was maybe 4 or 5 years ago now, where I proved via different methods a quantitative version of this theorem of Berger. So showing, under the same assumption, alpha less than D, that you have some power law bounds, like the probability the cluster at the origin has size at least n is bounded by some power of n that was not optimal. To write this paper, I had to write the introduction, right? You have to do your literature review. And I actually didn't know about NUM's results, so I was pretty disappointed when I found out the continuity was already known. But yeah, anyway, so, you have to find out, okay, what are the conjectured, like actual powers? Like, what does the physicist say about them and so on, right? What I discovered is there were these like amazingly nice conjectures that I'd never heard of before. And so this really got me like hooked on this problem. Like, okay, there are actually, the point is there are these models that they have this low dimensional regime, basically this one here, this effectively long range low dimensional regime, in which some of the exponents have simple explicit values, at least that was the conjecture. So let me tell you about that. Okay. So I normally credit this to Sack. Sack is a physicist. He was working in the early 70s. But his prediction is a refinement of an earlier prediction by Fisher, Ma, and one other person whose name is escaping me. And he was working not on percolation, but for Ising or something. But it's the same story. So what we're going to want to understand is the 2-point function exponents. Right, so remember, this was denoted this way traditionally. And as a warning, for nearest neighbor models, we kind of justified writing it in this way by saying eta is like the correction to Green's function scaling. But of course, it's the correction to Brownian Green's function scaling. So for long range models, you no longer expect eta equals 0, right, in high dimensions. Okay. So this is the definition of the exponent. And Um, so let's fix D. I'll take it larger than 1 for now, and then I'll say what happens in 1 dimension. Want to understand how does this 2-point function exponent depend on alpha? Okay. Now, I'm going to give you a pretty bad reason for this prediction, and I'm not claiming that this is what Sack was doing. You know, he had a much more principled way of arriving at this guess. Okay, but first thing that's very reasonable, if alpha is large enough, presumably at some point, the kernel is decaying fast enough that you behave the same as the short-range model, right? That's certainly, you know, as we were saying, for random walk, this happens when the variance becomes finite. Percolation, maybe, I'm not sure when it happens, but eventually you'll start to behave the same as the nearest neighbor model. So let's say that happens at some alpha c, and you know, once you get to alpha c, your value should just become it should no longer depend on alpha. And of course, this value should be whatever the short range value at this exponent is. Okay. Now, on the other hand, if alpha is very small, so I was telling you before about, you know, this notion of effective dimension, right? And you can see that, you know, as alpha goes to 0, the effective dimension diverges, right? So in particular, you know, if alpha is very small, you should have high dimensional type behavior, like mean field behaviors, maybe better to say. Okay. Well, what does mean field behavior mean? Well, it should mean that critical percolation behaves like critical branching random walk. But again, that's now the long range branching random walk, right? So that means that the 2-point function should be behaving for small alpha like the Levy process Green's function, right? Which is for alpha less than 2 is x minus y to the minus d plus alpha times a constant. Okay, so what that means for small alpha, you should see just this straight line, right? 2 minus eta equals alpha, in other words. Okay, so the conjecture is actually just that these are the only 2 parts of the curve. So you just join them up continuously. And again, that's, you know, he didn't just say that. He had a reason. But this is the conjecture. Okay. So, you know, in 1 dimension, it's the same. It's just that you only get this straight line, and then you no longer have a phase transition. Okay. Okay, so a couple comments about this. One thing, of course, if you believe this prediction, then it says that you know what alpha c is in some sense, right? It's 2 minus the short range value of eta. Okay, so you know, one warning is that, of course, this graph is extremely simple, apart from that the location of this corner is a number that's very difficult to understand, you know, in low dimensions, right? But you know, in high dimensions, this should mean that alpha c is just equal to 2, which is this finite variance thing. It's the same as the branching or simple random walk. Okay, but in low dimensions, it should mean, you know, eta should not be 0, and then you should have a different location of this crossover exponent. Okay, and you know, numerically, and also according to these expansions and so on, alpha c should be slightly larger than 2 when d is slightly smaller than 6. In fact, you know, the derivative should be 1/21, so not very much larger than 2. And then it actually becomes slightly smaller than 2 in 2 dimensions because it's 2 minus 5/24 in 2 dimensions, conjecturally. Okay. Now, so one thing that you don't see here is that there is actually no special role for this point d/3 in this drawing, right? So this is where, like, the mean field, let's say they're this way around if you're below 6 dimensions. So this is where mean field behavior ends, but actually the two-point function does not detect the difference between the mean field and non-mean field regimes for this model. Okay. Now, on the other hand, once you have this prediction, you can use, I mentioned before about scaling relations, hyperscaling relations, so on. So there are other predictions that you can make by just plugging this prediction into those relations. So just having one exponent actually is not sufficient to determine like all of the exponents. So for many, if you look at the most standard ones, there are actually 2 degrees of freedom in low dimensions. And it appears that the second degree of freedom, if you like, is not supposed to have an exact simple expression like this one does. But one other exponent that you can compute using just this one plus the scaling and hyperscaling relations is delta. So recall this is the volume tail exponent. Okay. And let's say D is between 1 and 6, although similar drawings are available in other dimensions. It should look like this, where this is D over 3. So of course, alpha equal D over 3 is when the effective dimension is 6, when D is less than 6. This is alpha C. This is the short range value of delta, which can be expressed in terms of the short range value of eta, assuming the validity of these hyperscaling relations. This is 2, which is the mean field value. And then this curve in between is what you get by applying these relations to this straight line. And it's the hyperscaling relation, so it's only valid in below the critical dimension, which is why you don't get the same curve down here. And you get D plus alpha over D minus alpha. Okay. So in one dimension, the conjecture would just be, you just get the first 2 parts. So you get that it's equal to 2 and then equal to 1 plus alpha over 1 minus alpha. And I should stress again, as with many of the things I've been telling you about, this kind of phenomenon is supposed to happen across many different models of statistical mechanics. You should think that the numbers are going to be different maybe, but actually if you just look at this version with the 2-point function, basically the conjecture for many models is that you just get this line, a 45-degree line followed by a horizontal line, and the location where they meet has to be the one given by the nearest neighbor value of eta. Right. Of course, that is what happens for simple random walk, right? Like in that case, we were saying the Green's function for the Levy process is minus D plus alpha. The Green's function for like general alpha walk is, well, it's basically minus D plus the minimum of 2 in alpha with a log correction at alpha equals 2. Okay, so that's exactly this curve. And yeah, maybe I can mention, that there was some physics papers. Sometimes you'll hear it said that this is a somewhat controversial prediction. I think the controversy is generated on the basis of some quite bad research. So what you can do is you can try testing these things numerically, right? And of course, it's very natural to do. And if you do that, you really don't see this curve at all. You see something much smoother, something like this. And this led some physicists to claim, just on the basis of simulations, I think, that this stack conjecture was wrong and that there should really be like a middle phase where you have some different behavior. But really, the thing is that, generally speaking, like computing critical exponents from simulations, it's just very computationally expensive, even in the best of situations. But around these points, the convergence is even slower. Like basically, you should think presence of logarithmic corrections and stuff like that or being near the presence of a logarithmic correction means that you should have even slower convergence to critical exponents. So, and indeed, what you can do is you can take the same methodology of that physics paper and do it for simple random walk. You'll also see this graph with the nice smooth curve. But of course, it's very easy to prove that the Green's function for simple random walk has exponent minus d plus minimum of alpha and 2. So anyway, you know, I think in math we used to you know, only getting the cream of the physics papers coming through, and you know, if you start digging by yourself, you might find some less high quality stuff. Anyway, okay. All right, so I can start telling you about the progress we've made on proving uh, these conjectures over the last few years. Um, so uh, So the development of the Euclidean theory, like on ZD, has been done kind of in parallel to work on the hierarchical version of the model, which is a sort of easier version with a different kind of symmetry that's more appropriate for the study of this kind of thing. I think I will suppress that story a bit and just tell you about the Euclidean story because it's going to be less confusing to not switch between different models all the time. But basically, what I'll say is that, you know, every time I state a theorem about ZD, you can imagine inserting like a hierarchical version of the same theorem that comes like 2 years earlier, something like that. Okay. So, um, okay. So, as I mentioned, the first thing I did on this was just to prove some power law estimates under the assumption alpha less than d without the right exponents. And I don't remember what those are, so I'll skip ahead to the next theorem. I think this was from 2023 or 2022, was the following. So if alpha is less than d, actually this theorem is going to be vacuously true if alpha is larger than d as well, but let me say it anyway. Then if I look at the average of the 2-point function over a box of side length r, then it's bounded up to constant by this. So what you should think in terms of the exponents is that, you know, that we have this is the conjecture, and this is the theorem, basically saying that the exponent is upper bounded by the straight line that you get in the first part of the curve. Okay. And the proof has this annoying caveat that it doesn't let you bound the 2-point function pointwise, but only the averages over boxes, which is actually quite annoying. So, you know, if you had the pointwise version, you would be able to deduce, for example, that the triangle condition holds when alpha is less than d over 3. This actually does not, as far as I can tell, imply that. But anyway. So the proof of this is something I could give you the full proof of over the next 2 days. I have to decide which proofs I want to show you, I guess, but it's within the scope of something we could do in the remaining time. So, you know, when I wrote this paper, so again, this was based on earlier work I did on the hierarchical version of the model. And in the hierarchical version, you actually get matching upper and lower bounds. And one way of thinking about it is that these hierarchical models, they don't have this transition to an effectively short-range regime. They always behave effectively long-range, right? So, in this picture, we should have, in mind that this is the effectively long-range regime. This is the effectively short-range regime. Okay, so I put at the end of my paper, well, it's obviously would be very nice to have some conditions under which you can prove a matching lower bound. And Noam Berger and his then student Johannes Baumler took maybe like 2 months to write a paper doing this. So what they showed, look at the same quantity. Then if alpha is less than 1, then it's also lower bounded by something of the same order. If alpha is bigger than 1, then they just get the bound minus d plus 1. And in the marginal case, they get with a log. Okay, so what you can think is that what their theorem is telling you is it's also giving you a lower bound in this picture, which is of the function of the same form as the conjecture, but where this kink is in presumably the wrong place. Okay. This is a 1. Okay. So okay, so maybe I can give you some. Well, but before I do that, let's just say, as a corollary, of course, is that if alpha is less than 1, then you have matching upper and lower bounds, right? So this average is really up to constants given by what it should be according to this conjecture. And in fact, just a year or so ago, I showed that, in fact, under this assumption that alpha is less than 1, you can really get a pointwise bound. Okay, so this is kind of proving the conjecture for small values of alpha. But one thing to say here is that, well, in d equals 1, this is the whole graph, right? Like alpha equals 1, there's this discontinuous phase transition. Of course, the minus d plus alpha is 0, so you get non-decay, right? It's consistent with that. And so this is the whole conjecture. Okay. So, this is really you're completely solving the problem in 1 dimension. And just to stress, this is really an analysis of models which are not always mean field, right? So in 1 dimension, their mean field up to alpha is a third, and then their non-mean field, you're in this effectively long-range, low-dimensional regime until alpha is between 1/3 and 1. Oh, one thing I should have mentioned before, but I forgot to, is that all of this stuff you can imagine in high dimensions. So when the effective dimension is strictly larger than 6, you have all these techniques that I mentioned, like the lace expansion, right? And these have been successfully applied to long-range models with the same caveats as they have for nearest neighbor models. So this was done by Marcus Heidenreich, Remco van der Hofstad, and Akira Sakai, and then there was more recent work of Akira Sakai and with Chen. And in particular, if the effective dimension is strictly larger than 6, and you have some numerical assumptions on the kernel, so it's a bit confusing, this distinction between these spread out models I was talking about before, so like large finite range versus long range, which is infinite range. So you can also do long range spread out, which basically means that the kernel looks flat up to, it looks like it's not decaying up to some large scale. For these kind of models that are spread out enough, they can analyze them with the lace expansion. And then, once you're doing that, you can prove everything. And a key thing to stress about these new theorems is that they do not have any of these numerical assumptions. There's no additional assumption hiding here that I've not written on the board. This is really the theorem. In fact, really the theorem is more general because they don't require exactly this choice of J that I wrote down. So in one dimension, this completely resolves the conjecture about the two-point function, and in two dimensions, it treats this regime between 2/3 and 1, where the model is not mean field. Okay, for the two-point. In fact, maybe so maybe what we can do the remaining time of today is I could prove this upper bound to you. I think I can definitely do that in before 12. Okay, and then we'll have seen some proofs, so we'll be happy, and we're not just adding 4 to 2 or whatever and pretending to be physicists. Okay, so let's try and prove this upper bound. Well, hang on, no. Maybe I want to do the hierarchical version. Yeah, let's do some hierarchical stuff. Okay, I've changed my mind. Okay, so what is the hierarchical lattice? Okay, so basically what I'm going to do is I'm going to replace the metric on ZD with a different metric. So you can think when we define long-range percolation, it's not really defined on a graph. It's defined on, well, a space with a kernel, right? So if I replace the norm with a different metric, it defines another long-range percolation model, right? So what we're going to do for the hierarchical model is I'm just going to define a different metric on ZD. So let's do, for example, H22. So the D is the dimension, it's going to be still kind of on ZD, and L is like the arity or adic, it's going to be the L-adic hierarchical model. So let's do the dyadic one, right? So let's suppose we have Z squared. Okay, and then what we're going to do is dyadically partition it into boxes. So, you can think, well, the points start off as their own box that just contains themselves, if you like. And then we'll split into 2x2 boxes. And then 4x4 boxes. And of course, we have some choice in how to do that, right? Because maybe, let's say we have some more 2x2 over here. Maybe I draw the 4x4 here, and so on. Okay. And we just keep going. So, at each point, the boxes at the next scale should have the boxes at the previous scale like nested inside them. Okay. And what we're going to do is I'll define the hierarchical distance. So I'll write it like a norm. It's not really a norm. Of course, this completely breaks the translation invariant, but just so we have some notational harmony between what we were doing before. I'll define the distance between X and Y to be the side length of the smallest distinguished box. Okay, containing both points, obviously. Okay, and I'll call these distinguished boxes, so the ones that are actually used in the hierarchy, in the dyadic decomposition, I'll call these blocks, just to have a word for it. Okay, so this defines a metric. Again, it's not really a function of X minus Y. This is just abusive notation. Okay, and what you'll see is that the hierarchical distance is at least the Euclidean distance. I guess it's at least the L infinity distance or something. But right. In general, it's larger, right? If I have these 2 points here, well, actually, I didn't draw enough stages of the decomposition for it to even be determined what the distance is, right? But the distance is at least 8, right? Because maybe I merge these into a box, an 8 by 8 box on the next scale. Okay? But they have Euclidean distance 1. Right, so what you should think is that for like generic choices of points, the hierarchical distance is of the same order as the Euclidean distance, but for some points it's much larger. Okay. Now, one way you can think about this is that this way of defining the lattice. So of course, if you have D and L, D is just the dimension of ZD. L is the amount by which you increase the side length at each scale. We've kind of imposed this structure onto ZD, but in some ways it's a bit unnatural. And another way you can think about these things is that they're metrics on the leaves of a tree, right? So you can think, for example, if you did this in 1 dimension, right, then okay, you have these points, and you're splitting them first into intervals of length 2, then splitting those into intervals of length 4, and so on. And you can think of this as having the structure of a tree, right? So where the actual points of your space are the leaves of the tree, and the internal vertices of the tree are the blocks, right? So you have this, and this, and then I didn't tell you how to keep partitioning them, but maybe it's this and so on. Okay. Right. Although I should stress, although you can think of the hierarchical model as like, or the hierarchical space as being the leaves of a tree, when you do these long-range statistical mechanics models, you shouldn't really think of it as a model on the tree, because you have all these like long edges going. Percolation on a tree is a rather trivial thing, and long-range percolation on the hierarchical lattice is not. Right? They're quite different. Okay, good. So the nice feature of this model is that it's very well suited to these kind of renormalization type things where you want to go up a scale, understand how things are changing as you go up each scale, because you have this very simple recursive structure of these blocks, which is that you can think, if I take the block twice as big, say, and twice the diameter, in this case. Another way of saying it, if you say, let's say lambda n is the n block, so side length L to the n, containing the origin, right? Then lambda to the n plus 1, you can also think about constructing the space recursively, where you say, when you go up a scale, you take a disjoint union of L to the d copies of the n block, and you set all unassigned distances to be L to the n plus 1. Right? So in other words, when you go up a scale, every point in this box here has the same relationship to every point in this box here and here and here, right? There's no difference between the things that are meeting on the boundary, the things that are in the bulk. You have complete symmetry in that regard, okay? So you can think basically, that there's a number of reasons these hierarchical models are relatively easy to work with. One is that they kind of have a lot more symmetry. I mean, strictly speaking, it's just different symmetry, right? I mean, they actually don't have the symmetries of ZD, but they have, in some sense, a lot more symmetry. The other thing is this ultrametric property, which is basically what's going to prevent them from ever having an effectively short-range regime. So, we won't have to understand these corners that we're taking, which are somewhat mysterious. And they have this nice recursive structure. Okay. Yeah.
Now do this in the hierarchical lattice because that's the fun part, and the other part is hard work.
It's also fun, but it's I'm not sure I'll be able to explain it in an hour, and it's easier to explain this and then tell you how to change it. Yeah, I'll hopefully be able to give you at least some indication of how you can change it. In fact, what we'll see is that a lot of the proof just goes through, and then there's one thing at the end that doesn't. But in order to fix it, you have to go back to the start and change loads of stuff. Okay, so all right. So of course we can now define long-range percolation, exactly like we did before, right? So it's just going to be, 1 minus e to the minus beta, but now it's the hierarchical. Okay, and this hierarchical lattice is still transitive, right? Again, it doesn't have the symmetries of ZD, but it is transitive. Okay, and the theorem that we'll be able to prove is that if alpha is less than d, then for the hierarchical model, this is up to constants minus d plus alpha. Okay, so again, was where it's confusing. So the edge kernel is minus d minus alpha. The connection probability via path is minus d plus alpha. Okay. So again, you can think these hierarchical models, they just do not have this transition to an effectively short-range regime. On the other hand, if alpha is bigger than d, then they don't have phase transition. So maybe I'll just mention that for the hierarchical model, beta c is finite if and only if alpha. Okay. So maybe just to say briefly where this alpha versus d thing is coming from. It's also, why it's a important condition in ZD as well. Is that if you take two boxes, let's say they're side length n, and let's say for ZD purposes that they're also separated by distance n. Actually in the hierarchical case, boxes are always separated from each other, so you don't have to say that. You can say how many edges are there in expectation between these two boxes, right? Well, basically each potential edge is there with probability n to the minus d minus alpha. And how many boxes are there? Well, how many points are there? Sorry, there are n to the 2d, right? So I get n to the d minus alpha. So this is large when alpha is smaller than d. It's order 1 when alpha is equal to d, and it's small when alpha is larger than d. Okay, so one way I like to think about this transition between the effectively long-range and short-range regimes is in terms of like, if you take two large boxes next to each other, you can say, how do the large clusters on this rectangle like form out of the large clusters in the two boxes, right? You can imagine one strategy they take is that you have these kind of nicely equidistributed clusters, and they mostly just join by some like bulk to bulk, like long edges, right? Another thing they could do though is maybe they both go near the boundary a lot, and they mostly merge by short edges, right? So, you can imagine that probably either one of these two strategies will be dominant. Okay, at alpha c, maybe like all scales, distances from the boundary are equally important. You get logs and so on. It's more complicated. But for like a generic choice of alpha, probably just one of these two strategies is dominant. You can think in the strategy where bulk to bulk is dominating, this is going to be the effectively long-range regime. The strategy where boundary to boundary is dominating will be the effectively short-range regime. And in these regimes, presumably you behave the same as a model that only has that kind of interaction, right? So once this starts winning, it's plausible at least you start to have the same critical behavior as the nearest neighbor model, which you can think only has the boundary to boundary, the short range interaction. When the long range effects are winning, it means maybe you behave the same as the hierarchical model, which is exactly the thing that only has bulk to bulk. There is no boundary, right? In the hierarchical case, these points are not close. These points here are not closer to each other than these points here and here. Okay. Okay. So yeah. So what happens is, if alpha is bigger than d, then like not only will you not have infinite cluster, you won't even like even the just boxes won't be possible to leave a box at all. Like even without getting to that edge first in the hierarchical case. Okay. So let's start proving this theorem. Maybe I'll start with the lower bound. Actually, the lower bound here is very easy. Although, it's of course the lower bound which does not generalize to the Euclidean model, at least not always. So here's a fact. So let's suppose that S, this fact will be for a general transitive weighted graph. Suppose S is a finite set containing the origin. Okay, you can define what's called phi beta of S. So some of you will recognize this notation this is from the Dumno-Copan-Tassion proof of sharpness, the phase transition. Right, so it's going to be the sum of edges in the, let's say, oriented edge. So these are the edges with, the E minus will be inside S, E plus will be outside S, of JE times, I think I actually want the probability E is open, times the probability that the origin is connected to the endpoint inside S, inside S. Okay, so this means using an open path, only using vertices of S. Okay, and the fact is that at criticality, this is at least 1 for all finite sets S containing the origin. Basically, the reason why is if you have a set that has this quantity is less than 1, then you can embed a subcritical branching process or you can embed percolation inside a subcritical branching process and deduce that you don't have infinite clusters. And then there's just continuity argument, right? So phi beta of S has to be at least 1 for beta larger than beta C, but by continuity, it's also true at beta C. Okay. So the nice thing is for the hierarchical model, this actually just implies the lower bound on the 2-point function because you just plug in this n block, right? And what you see is that when you have this M block, the nice thing is that every vertex's contribution to the boundary is the same, right? So in other words, if you have V in lambda n, the sum of edges of JE over edges where E minus is equal to V and E plus is not in the block, this is a constant. It doesn't depend on the choice of V, right? This is like one of the things that makes hierarchical models much easier, right? And you can compute that this is, well, let's just do it. So we're summing over scales which are larger. So from n plus 1 to infinity, right? We can say for each scale, how many points can we connect to there? Well, it's like L to the KD, right? The probability that that edge is open, yeah, or the JE, which is the same thing, is minus D plus alpha, sorry, times, sorry. Okay. Right. So, this cancels with this. I just get minus alpha k. So geometric series, so it's just roughly L to the minus alpha k. Or, sorry, n. Right, the bottom of the series. Okay. So what this means is that this quantity here, up to constants, is just L to the minus alpha n times the sum over the box of the probability that the origin is connected to X inside the box. Right? And we said this is at least 1. Right? So of course we can just rearrange this and we get that this guy, this sum, is at least this. Right, but this is essentially equivalent to the 2-point function bound that we wanted to prove. Of course, you have to be a little bit careful because this is an average. In fact, let's just restrict ourselves to proving average versions. In fact, what happens for the hierarchical model is because they have so much symmetry, you can actually just, the average bounds imply the pointwise bounds, actually. They have the property that any 2 points at distance n can be mapped to any other pair of points at distance n by an isometry. So they're what are called distance transitive. Like the isometry class of a pair of points only depends on their distance. And that just means that, average bounds automatically become pointwise bounds. Okay. Okay. And maybe just to say something briefly about what Noam and Johannes did. So, of course, if you try and apply this argument in ZD, the thing that goes wrong is that, well, it's no longer true that this is a constant, right? Like the, points near the boundary have a lot more weight of edges going outside the set than points in the bulk, right? And so what they realized is that instead of applying this inequality to a ball of fixed radius, you apply it to a ball of random radius between n and 2n, and then you take averages everywhere here, and then it actually, when alpha is less than 1, it does become the case that you do successfully average out this effect, and basically it becomes as though you were dealing with a constant here. When alpha is larger than 1, it doesn't work anymore. Okay, so let's try and prove the upper bound. Okay, so we're going to start off by considering a different quantity. So I'm going to define Mn. Roughly, it's going to be the typical size of the largest cluster within a ball of within the n block. for reasons that I regret, instead of using the median, I used the 1 over E quartile or whatever you want to call it. So except that it's now been independently suggested to me by two people that this should be called the Edian. So I actually quite like this now. So this will be the Edian of, and I'll say what that means in a second, of the largest size of largest cluster in the n block. Okay, so what do I mean by that? I mean it's the infemal value of n such that the probability that there exists a cluster in, this depends on beta, obviously, in lambda n of size at least n is smaller than 1 over e. Right, if this was a half, this would be the median, right? And so it would be convenient to say equivalently, I'll define k max n to be the size of the largest cluster in the n block. Of course, there could be more than one cluster of maximal size, so it's not really well defined as a set, but its size is well defined. So this event is just this. Okay. So our first proposition is that Mn of beta c is big O of L to the d plus alpha over 2 times n. Okay. Now the way we're going to prove this is via kind of an inductive approach, sort of this cascading kind of thing. I think I called this a runaway observable argument. So the idea is basically to say, if this bound is ever exceeded too badly, you know, there's some constant here, on some scale, then it will start to become exceeded much worse, you know, and start blowing up very rapidly as you go to larger and larger scales. And then we'll just say, like, this cannot happen. So the key lemma is going to be this thing saying, if it starts to be exceeded on some scale, then it continues to be exceeded. So, okay, let's see. There exists L naught less than infinity, such that for all L least L naught, there exists a finite such that following holds. So if the claim is going to be an implication, so it's going to be if this, actually, let me put this square in. If this holds, then at some scale n, then the same bound at the same form continues to hold at scale n plus L. Okay, now of course the proof will really show that, you know, if this holds at some scale n, then it will actually be growing much quicker than this as you go up the scales. But you know, it's convenient for the proof to just prove a bound implying itself. It's just simpler for doing induction with. Okay, so before I prove this lemma, let me explain why it implies the proposition. Um, okay. So the first thing is that if beta is actually strictly less than beta c, right? So I mentioned this theorem a couple of times, the sharpness of the phase transition. So, that either says the expected size of the cluster at the origin is finite below beta c. In fact, that implies an exponential tail, which you either get directly from the proof or from these tree graph inequalities, which tell you have an exponential tail once you have finite mean. So if beta is less than beta c, then you have this exponential tail on the size of the cluster at the origin. And just by doing a union bound, what you'll get is that mn is big O of like log of the volume of the box, right? Which is order n. Okay. Now the sharpness of the phase transition, it doesn't give you any control of like what the constants are here, how they blow up as beta goes to beta c, and anything like that. But what we want to do is basically use our lemma to extract sort of quantitative information from this qualitative statement. So here's the idea. So what it suffices to prove that mn beta is strictly less than squared over beta for all beta less than beta c and n at least one. Why is that? Well, then we just take a limit, right? Okay, the median or the median is like not continuous, so there's a slightly annoying thing, but it's continuous up to like adding one or something. So let's not worry about that. But basically, the point is, if we have a statement like this, we can't just take beta to beta c because we have no idea what the constants are doing here, right? And of course, this bound, like it won't be of this form of criticality. But here, the dependence on beta is controlled, right? I mean, in fact, this constant is getting better as beta gets larger, right? So you're in a position where you can take the limit. Okay. Why is this true? Well, if not, so if this goes wrong for some n and beta, then the lemma set tells you that mn plus kl, apply this with L equals L naught, is greater than or equal to A over beta L to the D plus alpha n plus KL, for all K at least one. And of course, this bound is not consistent with this one. I mean, the constant here could be huge. So, maybe you don't get a contradiction at the scale you started with, but you have this for infinitely many scales. At some points, it will become inconsistent with this. Okay, is that clear? Okay. Okay. All right. So now we have to prove the lemma. Okay. And I guess before giving you the proof, let me explain like what is the significance of this d plus alpha over 2 bound, right? So you should think, suppose I have my block here and my block here, and I have some cluster here, and so but maybe the largest cluster here and the largest cluster here, right? You can say, okay, when I increase the scale, when I go to the next scale, what's the probability, or what's the expected number of edges that get drawn between these two things, right? So let's call this cluster A and this cluster B. Well, each particular edge, it's the same computation we did before with the whole boxes. Each particular edge is there with this probability, right? And then I get the size of A times the size of B for the number of choices. Okay, so this bound, the largest cluster size is big O of sorry, of L to the D plus alpha over 2 of N. What this is saying is that this merging probability cannot be high, right? It's like maybe I have a good probability that the largest cluster here merges with the largest cluster here by the addition of a single edge. Maybe it's low, but it cannot be high. That's what the proposition is. Okay. So what's the proof? So, okay, we know, let's say we look at the N plus L block, right? So we have L to the D to the power L copies of lambda N in lambda N plus L. Okay, and we know each copy has a large, cluster size at least. Okay, there's this annoying off by one thing because of some continuity things. I'll almost ignore this, but a size at least this, with probability at least 1 of E. Okay. Or 1 minus 1 over E, I guess, or whatever. It just doesn't matter. I'll just write C. Okay. So what we can do, of course, is use the weak law of large numbers. Okay. And we can say that, there exists L1, say, such that if L is larger than L1, then at least, let's say, 1/10 of the copies contain a large cluster, large meaning larger than this, with probability at least, sorry for going into corner law, something very close to 1 minus epsilon, right? Let's just use non-type constants. I'm not trying to optimize this, right? This is just the weak law of large numbers, right? We're just saying each one of these things, they're independent. Each one has a good probability of the outcome we want. If we take a large number, it's very likely that at least some fraction of them, if we take the fraction like lower than the thing that we care about, then we'll have a high probability of the event that we want. Okay, we're just doing something completely trivial. Okay, so let's now look on this event. Okay, and so we have this large number, some linear number of the boxes contain these large clusters. Okay, now if I look at any two of them, and of course they could be quite far away from each other, right? Because I picked maybe a big constant here. What's the probability this guy merges with this guy? Well, let's say if Mn is larger than Mn squared is larger than this, where A is a parameter for now, we're going to take it to be large soon, right? Then, well, what's the expected number of edges between these two large clusters? I'll ignore this -1 because it's just a nuisance. So, the expected number of edges between two large clusters is at least, well, it's their size squared, that's the number of points. And then I have this probability each particular edge is there, which, okay, I get a factor of beta to be more careful about the inclusion probability of the edge. And I get, this is up to a constant L to the minus D, D plus alpha times N plus alpha. Okay. All right, so in particular, we can pick A as a function of L large so that the merge probability is close to 1. Okay, so you can think we're getting kind of Oda-Shreni random graph like on these large clusters, but actually we're going to analyze the Oda-Shreni in the very trivial regime where P is very close to 1, right? So we can even take this probability so close to 1 that with high probability every two things are just directly connected by net. You don't need to worry about phase transitions in Oda-Shreni or anything like that. Okay, so again we can take the merge probability to be close to 1, but then the number of these things is also controlled by L, so taking A even larger, we can say by taking A large enough, all large cluster, i.e. the largest clusters in each of the good boxes merge, let's say with probability at least 0.999. Okay. All right, so what happens is that we found this good event, right, that has probability at least 0.998, if you like, right, on which we have a good supply of these boxes in which the largest cluster is large, and all of those clusters merge together, right? And the only important thing about 0.998 is that it's larger than 1 minus 1 over E, right? So what we get is that for this choice of L, M of n plus L is at least, this assumed bound that we had on each one, d plus alpha m, multiplied by the number of these good boxes, right, which we said was going to be like 1 over 10 or something times the total number of boxes, which is n L to the dl. Sorry, this is over 2. This is okay. So maybe I'll square everything to make it look a bit nicer. Okay. Now, what's the point here? Well, we're going to win because alpha is smaller than d, right? So, this exponent here is beating this exponent here. So in particular, there exists L naught bigger than L1, such that if L is at least L naught, then 1/10 L to the 2d L is bigger than L to the d plus alpha. Oh, this is just because alpha is smaller than d, right? So if we use this choice of L naught, again, we're always choosing A to depend on the choice of L, then we're done, right? So we kill this, sorry, 100. We kill the constant. Okay, and that's the proof. Right, so we're really doing like very sort of trivial probability stuff here, right? I mean, just weak law of large numbers. That's it. A union bound here, basically. Okay. Okay. Okay, so that gives us that proves the lemma and therefore the proposition. Okay. So, at this point, what have we learned? We've learned this bound on the median of the largest cluster size. And we don't tend to use medians or medians for that matter very often, really, in most things I work on in probability because they give very weak information. So, having a bound on a median might not be very useful, unless you know something else, right? Unless you know some kind of concentration or something. And it turns out that for this particular problem, you actually can extract useful information from the median or the median. So this is via something called the universal tightness theorem. It's universal because all the constants are universal. It's tightness because it's establishing a form of tightness. So this was actually something I introduced in my first paper on long-range percolation, which proved these non-sharp power law estimates. So this particular thing from that paper has been very, very useful for many other things. So this is something about, we're going to go back to percolation on an arbitrary, there's any weighted graph. Okay, and we'll take lambda to be a finite set of vertices. And you're allowed to take lambda to be the whole vertex set if you're working on a finite graph. Okay. And what we will consider is k max lambda to be the maximal intersection of a cluster with lambda. Okay, so here we're considering the clusters in the whole graph, right? And just intersecting them with the lambda. Of course, if you want to consider clusters that are not allowed to leave lambda, you can do that too. You just use the different graph. Okay. And so the theorem, and we'll define m eta lambda to be this EDN of this random variable. So again, the infemal value of n, so the probability exceeding this is at least, sorry, is at most 1 over e. So here's the theorem. It has 3 parts. So the first is that it's very hard for the maximum to be larger than its median. I'll stop writing the lambdas just to make it, and the betas, just to make it cleaner. So the probability you exceed the EDN by a factor of lambda is at most e to the minus lambda over 9. Okay, so it's universal that, it's a universal constant. The constant 9 is not very important, but it doesn't depend on the graph. Secondly, the probability that it's smaller by a factor of epsilon is at most 27 epsilon. And finally, if I look at a specific vertex and I say, what's the probability that the cluster of this vertex is larger than lambda m? So m is still the EDN of the maximum, not of this vertex. This is bounded by the probability that it's larger than 1 times m times e to the 1 minus lambda. Okay. So again, you can think this is giving you this kind of shape theorem that's saying that this distribution is kind of bounded by like an exponential random variable or something like that. Now, in many situations, this bound is quite far from the truth. If you're looking at subcritical or supercritical percolation, actually the maximum cluster size will be very well concentrated. So, this is a tightness thing. It's saying that, it's on the order of something. In many regimes, it will actually be concentrated. And, if you apply this, like if you look at the critical Erdős-Renyi or something, I think maybe the actual tail of the maximum is like e to the minus x cubed or something. It's actually quite a lot faster than exponential. But, for the kind of applications that we'll be using this for, it's not going to be very important to know exactly what the tail is. The point is just that it's rapidly decaying. Okay. So, take time. So maybe I won't tell you the proof of this, just so I can finish the other thing in the rest of the time. But this is not very hard theorem to prove. So just to give you a brief overview of how the proof goes, it's a consequence of the BK inequality. And the key combinatorial thing is that if you look at this event that the largest cluster is larger than, let's say, n times 3 to k, something like this, it's contained in the disjoint occurrence of many distinct copies of this event that it's just larger than n. Right? This is a purely combinatorial fact. It's just something about graphs. It's saying effectively, if you have a graph of size at least 3 to the k times n, you can find a large number of disjoint connected subgraphs, edge disjoint connected subgraphs, which all have size at least n. Right? That's, again, just a purely combinatorial fact. And it's actually something you can prove by just proving it for trees, because you can take a spanning tree and then apply the lemma for trees. And the number of these copies is like, I think it's 3 to the, this is the kind of thing I would have to have written notes for to get correct, but it's something like this. It's roughly 3 to the k. Okay, and the point is, once you have this combinatorial fact, it's quite easy to deduce the first two parts of this theorem from this plus the BK inequality. It's just some messing around with the algebra. Okay. In particular, like for the first thing, it should be pretty obvious, right? If you take big N to be the Edian, right? This is saying to basically to exceed that by a factor lambda, right? When you apply BK here, you're going to get the probability you're bigger than the Edian, which is 1 over E. That's why I used the Edian, right? It gives you exponentials instead of powers of 2. Anyway, basically you're getting 1 over E to this power, right? So that's where the first thing comes from. To get the second thing, you have to do a little bit more algebra because you're going into tail in the other direction, but it's similar. And then similarly, if you look at a specific point, you have a similar thing. If you look at the cluster of a specific point here, then when you do this decomposition of your graph, one of those pieces is going to contain that point. And so, one of these will be this event. Okay, and then you get. Okay, so again, of course, I'm not giving you the full proof, but I've hopefully told you enough you could probably reconstruct it yourself if you spent some time thinking about it. Okay, so what is the point of this for us? Well, it means that this bound we got on that we just proved on the median is actually very useful. Right, so in particular, what this says is if you have a bound on the Edian, you actually have a bound on like all moments and with exponential tail and so on. And we're actually going to be applying this third part. Okay. So the way we're going to apply this is to say, if I look at a specific, like the origin, right, and I'll define Kn to be the cluster of the origin in lambda. And so now I'm going back to the hierarchical lattice. Okay. So it's a consequence of this theorem. This is exercise. But this is of the same order as if you restrict to the events that this is at most some constant times that there exists C making this true, right? The point is, this is the bound on the Edian, right? So this is saying once you go far enough into tail, it's not really contributing to the expectation anymore. This is something you can easily get from the third part of the scenario. Okay, so how are we going to use this? So what I'm going to do, so now I want to prove that at beta c, this should be for beta less than or equal to beta c. At beta c, this should be bounded by L to the alpha. Right? Of course, this is the same as the sum of this two-point function restricted inside the box, right? Okay. So again, we're going to prove this by proving a kind of inductive lemma, saying if this starts to fail, then it's going to fail much worse at larger scales, and that just can't happen. Okay. And in this case, the lemma that we're going to prove is that at scale n+1, you get a bound of this form. Okay. Now, why does the lemma imply the proposition? So in fact, in this case, we don't even need to use sharpness of the phase transition. So here's a little analysis exercise for you. Suppose you have a sequence satisfying an inequality of this form, so C times an squared over, say, alpha to the n, right? So there exists big C such that if an is ever larger than the exponential by this large factor, then an is actually double exponential, and it's growing at least like e to the something of order n, right? Basically, the point is, once this starts becoming large enough, the fact that you're dividing by the exponential is not doing very much, and you're basically just squaring every time, right? So if you square every time, you're growing like a double exponential. Okay. Now, of course, our expectation is the size of a cluster. It's at most the volume of the box. So it just cannot grow double exponentially. It's just impossible. You don't have to use any properties of percolation. Okay, good. So we just have to prove this lemma. Okay, so here's the idea. So let's take lambda n prime. So two neighboring boxes. In this proof, we just need to look at two. Okay, and we'll define curly C prime to be the set of clusters in lambda n prime. Okay, and I'll let script f be the sigma algebra generated by the clusters in lambda n and lambda n prime. Okay, so that should be okay. So what we're going to do is that, well, let's look at the expected size of the cluster at the origin. Beta will always be beta c for this proof. Look at the expected size of the cluster at the origin in the n+1 block, given f. Well, you know, I can always do this, right? I can have my cluster here. I can look at all of the clusters here, and I can look at all of the ones that I just directly merge to by just drawing an edge into them, right? So just by considering that way of contributing volume to my cluster, right, I get that this is at least the sum over clusters in the other box of their size, right? How much I win if I connected them, times the probability that I connect them, which is like something like this. Okay. Now what I can do is I can just say, well, you know, if I want, I can put in some indicators that things are not too big, right? So, you know, that's just going to make it smaller. Let me change my mind about this name of this constant. Right, so of course I can put this indicator in here. I can put these two indicators, and I guess I'll put this one as well. Right, and similarly, I'm going to put the same indicator inside the exponential. Okay, I can do that. I can certainly do that, right? I'm just throwing terms away. Okay, now, once I've put this in, you'll see that, you know, this thing that's in the exponential is bounded by constants, right? So, you know, in general, if I have 1 minus e to the minus x, and x is at most some x0, right? Then this is lower bounded by some constant depending on like 0 times x, right? I mean, like as x goes to 0, it's actually, you can take the derivative and so on, but we're happy to lose constants. So we're just saying, you know, the derivative of this is, you know, you're growing at least linearly in some sense of for bounded values. Okay. So what that means is that because we stuck this truncation in here, we can like linearize the exponential up to a constant. And what we get is, okay, we have this indicator again. I won't write the whole thing out, it's just the same one, times, and then what do I get? Well, I get this squared, right? Because there was one here that we're then linearizing and one that we had here, times the size of this cluster, and we also get the L to the minus D plus alpha times N, right? Okay. So now, of course, what you can notice is that actually this guy is independent from this guy. In fact, you don't really need to use that. If you do things a bit more cleverly, you can use FKG instead. But they are independent. So what we can do is we can take expectations on both sides. And we get, well, the expectation of Kn on the indicator that it is smaller than this. And then we also get this expectation of the sum over c squared times the indicator again that it's smaller than the same threshold. Okay. Now, what you can notice is, you know, whenever you're summing over the clusters in a box, it's always the same as looking at the cluster at the origin up to a size biasing thing, right? So in general, if you sum over all the clusters in some graph of some function of them times their size, right? That's the same as summing over the vertices of f of kx, right? Because, you know, each cluster is being counted the number of times that it appears that, you know, that you have a vertex in that cluster, right? So if you look at, yeah. So if you look at this quantity and then use transitivity to say that every vertex is contributing the same thing, this is actually just the size of the box times the same thing. Okay. And I forgot my L to the minus D plus alpha from before. Okay. So what we get Well, we conclude the proof, right? So, this minus d here cancels with this. I get the L to the minus alpha n, which is the denominator that I claimed here, right? And then I get the square of this restricted expectation, but then I told you that that's the same order as the unrestricted expectation. Okay. Good. So, okay, so what have we shown at this point? So that finishes the proof of the lemma and therefore the proposition, right? So we're saying that what we've basically proven is that the sum of the probability sum over, let's write it in terms of the average of the connection probabilities inside the sets is bounded by what we, sorry, not n, L to the minus. Okay. And this is almost what we wanted to prove, right? Okay, there's this issue about removing averaging. Let's not worry about that. But the only thing that's left is to remove this restriction, right? Really, we want the two-point function in the whole of space, and we have an estimate on the two-point function inside the box. Okay. Now, in fact, everything we've done here works for ZD as well. And this is the point where the proof breaks for ZD. So to see that everything worked for ZD, the way we were always arguing is to say, like, if something gets too big on some scale, then it gets like even bigger when you go to larger scales, right? So, and the point is that Euclidean distances are always smaller than hierarchical distances. So whenever you go to the next scale, like the probability that you add an edge there in the ZD model, it's always larger than the probability you add the edge in the hierarchical model, up to some constant or something, right? So in fact, this fact that you have these larger things, it only makes these proofs work better because they're always like about this cascade effect, right? The analysis of the cascade effect. So in fact, this proof, okay, there's a slight issue that boxes are not transitive in ZD, and if you run exactly the same proof, it will really tell you if you take a box and you have to average over both points instead of just one of them. But if you do that, then you'll get exactly the same thing, okay? And it's just in this last step, which I'm not sure I have time to do today because I think I'm basically out of time, the proof goes wrong for ZD, but it's very easy to conclude here from hierarchical. How long do I have actually? I think I can do this in like 2 or 3 minutes, but that might be over my budget. Okay. So how do we conclude in the hierarchical case? Okay, so we want to bound the probability the origin is connected to X. So let's say X is in lambda n and not lambda n minus 1. Right, so, well, we can say, we can take a union bound over the first scale at which the 2 points become connected. Right, so maybe they're already connected in the first scale that they could be, or I have to sum over how many additional scales I have to go up to. Okay. So far, so good. Okay, so what's the idea? Of course, the first term I've already bounded, right? So I don't need to worry about it. Okay. And so let's look at one of these terms. So let's suppose, the origin is connected to X for the first time at some scale. So you should imagine I have some path like this. Okay. So what I can do is I can look at the first edge that is used by this path to leave the box of radius, the n plus k blocks. Okay. And I can do a BK thing, right? So I can do my usual thing. I'll take a union bound over what this edge is, apply BK here. So if I look at one of these terms, I can bound by summing over, let's call these 2 points A and B, right? So I have to have A is in the n plus k block, B is in the n plus k plus 1 block, but not the n plus k block, right? And I get a disjoint occurrence, right? The origin is connected to A, the edge AB is open, and B is connected to X. This is inside lambda n plus k. X is connected to B in n plus k plus 1, right? And then I also get this L to the minus D plus alpha n plus k plus 1. Okay. Now, what I can realize is that actually the sums over A and B I have control of, actually, right? The point is this edge probability actually does not depend on the choice of A and B, so these two sums just factor, right? So what do I get? I get exactly these, the sum over A is the thing I already have control of, the sum over B, okay, it's a subset of the thing I already have control of, so even better, right? So what I get is that I have the sum over A, I bound by L to the alpha times n plus k. The sum over B gives me essentially another factor of the same thing. And then I get the L to the minus D plus alpha times n plus k. I'll ignore the 1 because it's just constant. Okay. So what do I get? Well, this is L to the minus D minus alpha times n plus k. So this sum is just a geometric series. It converges. So it's the same order as the first term, which is L to the minus D minus alpha n, which is what I wanted. So that concludes the proof. Okay, and again, the thing is that this really does not work in ZD for this reason that this probability that this edge, these 2 points might be next to each other, right? And then this edge would have like probability of order 1 of being open. Okay, so again, it turns out you can fix this argument, but you have to go right back to the beginning, replace all the quantities like with sort of weird ad hoc variants of the same quantities, set up in such a way that you can still get the proof to work, and when you get to this stage, you're only allowed to add long edges in the sprinkling, and then it works. So I don't think I'll tell you about that because I'd rather tell you about this other newer stuff tomorrow. But yeah, thanks again for your attention. Yeah. Yeah, so I mean, it's generally very, well, you'll see some more uses tomorrow. But maybe I'll mention in addition to those that it's also been very useful for completely different things in, these other things I'll tell you tomorrow will also be about like understanding critical behavior and so on. But actually in some of my work with Philip Iso, my former student on percolation on finite transitive graphs, especially in the like for high degree graphs, we very often use this fact. If you have a giant component, then even if you look at the neighbors of a fixed vertex, it's very likely that you have like a locally linear size component, like just restricted to the neighborhood of a specific vertex with high probability. This is a consequence of this theorem, and we use this a lot actually for it. So it's a very different application. Yeah. No. Yeah. And of course, you very often want to apply this with lambda as like a box or something. So
this joint occurrence you mentioned, that's general graph, right?
yeah, exactly. It's just a purely combinatorial fact.